In this video, we're going to look at 4 different equations of state that describe the behaviour of gases. The first and most simple equation of state is the ideal gas law. Now, the ideal gas law is defined as the pressure of the gas times the volume of the gas is equal to the number of moles in the gas times the ideal gas constant times the temperature. And the ideal gas law is not very accurate, and this is because it works under 2 very big assumptions. It assumes molecules in the gas have no volume, and that there are no interactions between these molecules. As in the real world, molecules always have volume, and there is always interaction between molecules. The ideal gas law is not very accurate. In attempts to fix this, a man called Johann van der Waals devised a new equation, where he found P was equal to RT over V minus B minus A over V squared, which introduced 2 new values, A and B, where A was the interaction coefficient of the gas and B was the molecular volume of the gas. What this does is it accounts for the assumptions made in the ideal gas law, which makes this equation much more accurate than the ideal gas law. But even this equation isn't perfect, as it fails to approximate the behaviour of gases as they near the phase change of a fluid. In an attempt to fix this, more equations of state were derived, the first being the Redlich-Kwong equation. The Redlich-Kwong equation applies more corrections to the van der Waals equation, making it much more accurate especially during the gas phase, but it does overcomplicate the equation somewhat. But even this equation fails in the liquid phase. Sought to better model fluids near their critical points, the Ping-Robertson equation was derived. This equation is much more accurate than the Redlich-Kwong equation and the van der Waals equation, especially for natural gases and non-polar molecules. A visible representation of the accuracies of these equations of state can be seen in the graph below, which is the volume in terms of temperature for toluene at 50 bar. This graph shows that the ideal gas law shows a very inconsistent model of the volume compared to all the other equations, which is to be expected as it is much less accurate than all the other ones. The other 3 all remain fairly consistent with each other, but they do differ somewhat. An important thing to take away from this video is that each equation of state has a time and a place, and you need to know when to use them, except the ideal gas law, which is terrible.